This problem, in part A, we're asked to prove that when a reference of the form R equals sin W0t is given, that the steady state error is equal to 0. So let's write down this part A of the problem. Let's write down the reference. It would be sin W0t. And we are asked to we're asked to prove that when we're given this reference, the error is equal to 0. This is a closed loop system with a unity feedback. Therefore, we can apply the following equation for error, which is equal to 1 over 1 plus GDCL by R, where R is the reference in terms of Laplace, the error is in terms of Laplace. And with this, we can find the transfer function of the errors when we are tracking only the reference. Okay, let's start by calculating this term here. So it will be EDS over RS equals 1 over 1 plus GDCL. Okay, if we do this algebra, we're going to find the following. We have EDS over RS equals 1 over 1 plus transfer function G, which is given here, 1 over S plus 1, multiplied by the transfer function of the controller, which is given in here. So it will be K S plus alpha squared over S squared plus W0 squared. Okay. Now, let's rearrange this and do some algebra manipulation. And we're going to have something of the following form. We're going to be working with the algebra to simplify this. We can multiply this denominator in here, in here, and in here. So if we do that, let's do that. Let's multiply this equation by S plus 1 plus S squared plus W0 squared. If we multiply here, we have to multiply over here too. S plus 1 plus S squared plus W0 squared. And over here. So S plus 1 S squared plus W0 squared. So now when we do that, we're going to have an expression of the following form. We're going to have S plus 1 S squared plus W0 squared over S plus 1 S squared W0 squared plus KS plus alpha squared, because all of this is going to cancel out. Now, we know that there is a reference input and we want the equation for error. So let's find the Laplace of the reference input, or the reference. So the Laplace for sin W0t is going to be equal to W0 S squared plus W0 squared. So this is equal to RS. So now let's multiply RS over here so we can get the error equation. So the error equation is going to be S plus 1 S squared plus W0 squared. And let me just put this a little bit up so you can see. And then we have S plus 1 S squared plus W0 squared plus K S plus alpha squared. And this is going to be multiplied by the reference, the reference. 0 squared, this is S squared. Okay. Now, this is the error. So if we apply the final value theorem to this error, we can find the steady state error, which is what we aim to find. So applying final value theorem, okay, when Wn equals W0, we're going to find that the steady state error is equals to the limit when s goes to 0, s, and therefore if you multiply this equation by s, when s goes to 0, ESS equals 0. So we have proved now that indeed when you use a reference of the form that sin W0t as given previously, the steady state error is going to be 0. Now let's work with part B of this problem. In part B, we are asked to find what are the ranges of k so that the system is stable using the Routh Routh criterion process. To use the Routh criterion process, we need to find first the characteristic equation at the tracking of error over R. So we already find that that equation was of the following form. It was s plus 1 squared plus W0 squared over s plus 1 squared plus W0 squared plus k s plus alpha squared. And then, so the characteristic equation will be the denominator of this transfer function. So we need to simplify this a little bit. So let's start by working with these two terms here. So basically, these two terms can be simplified as following. So we got s squared plus s multiplied by s squared plus W0 squared. And then that will give us the following equation. Now, let's then simplify this. So we know that the square s plus alpha squared is equal to s squared plus 2s alpha plus alpha squared. And all of this will be multiplied as here by k. So now we have we can put the characteristic equation is of the form, the following form. So we have s to the 4 plus s squared W0 squared plus s to the cube s W0 squared plus s squared k plus k 2s alpha plus alpha squared k. Now, let's rearrange these so we can group by factoring by the different s. So if we can factor this by s, our characteristic equation will be s4 plus s to the cube plus s squared k plus W0 squared plus s W0 squared plus 2k alpha plus k alpha squared. So this will be our characteristic equation to use in the Routh criterion. So I'm going to explain a little bit now how to do the Routh criterion process. So basically reviewing how the Routh criterion process works. So I'm gonna explain that a little bit in order to continue working with the problem. Okay, now let's identify what are the coefficients to use in the Routh criterion. So the Routh criterion define this as A0, this will be A1, this will be A2, A3, and A4. A meaning the coefficients of the terms of S. So this is S to the n, S to the n minus 1, S to the n minus 2, and etc. So now I'm just going to write the process, and then we're going to start solving the problem. So the Routh criterion define S to the n. You're going to arrange these in the following form: 1, A2, A4, A6. S to the n minus 1, the arrangement will be A1, A3, A5. and then s n minus 2. You're going to have b1, b2, 3, s n minus 3. You're going to have c1, c2, and c3. So that's how you're going to arrange the Routh criterion. And this is going to be about finding B and C's, so you can be able to get all the values in this arrangement. In particular, at the end, you're going to focus on the first column, and all the first column has to be positive so we can have a stability. So we're going to set those values positive in order to find K, and what are the values of K that made this first column positive. So let's start working with this. So let's accommodate these values for our equation. So we know this is our equation. So I'm going to start to accommodate the first values. So we will have S4, it will be 1, K plus W0 squared, and K alpha squared. Why? Because S4 is going to be, as here, S to the n, and is 1, A2, which is this coefficient, and A4, which is this coefficient. Okay? Similarly, I'm going to do S3, and now I'm going to have 1, W0 squared plus 2K alpha, and 0. Why? Because for n minus 1, I have a 1 coefficient, which is 1, a 3, which is this, W0 plus 2K alpha, and a 5, which is 0. There's no a5 in this equation. So I will continue with S squared, and S squared is going to be B1, B2, and B3. So I'm going to stop here, and I'm going to find B1, B2, and B3. So B1, we know that B1 is going to be equal to the determinant of 1A2, A1, A3 over A1. So from now on, all of these B's, we can find it then simply by recognizing in terms of B1, this is the matrix. We're going to find the determinant of this matrix, and we're going to divide it by A1, which is this value. Okay? So why? Because it's here. The matrix of this 1, A2, A1, A3 divided by A1, which is this value. So now, let's find B1. So B1 is equal to the determinant of the following values. 1 K plus W0 squared, 1 W0 squared plus 2K alpha, divided over 1. Okay? So when we solve this equation, we're going to have something of the following form. We're going to have cross multiplication of this minus this is going to give us K plus W0 squared minus W0 squared plus 2K alpha over 1. So when you simplify this, you're going to have these cancel out, right? So you're going to have K minus 2K alpha over 1, which is equal to K1 minus 2 alpha. So this is the value of B1 now. So we have B1 now. Now we have to find B2. So let's find B2. B2, similarly, we're going to use the same process, but now we're going to use the determinant of these and these over A1. So let's find B2 over here. So B2 is equal to the determinant of 1, 1, K alpha squared 0, because it's going to be 1, 1, and these values here over 1. So B2 is equal to K alpha squared. So now we have the value of B2. Finding B3 similarly, so B3 is equal to the determinant of 1, 1, 0, 0, because it's these values here, and these, and these values are 0, so we're going to have 0, 0, over 1, and B3 equals 0. So now we have B1, B2, and B3 values to plug in here, okay? So now we have to find, so let me just summarize again. So we have S4, 1, K plus W0 squared, K alpha squared. Let me just divide this in here. S to the cube, 1, W0 squared plus 2K alpha, 0. Square is going to be B1, which B1 we know that is K1 minus 2 alpha. B2 is K alpha squared. And then B3 is 0. Now, let's find C1, C2, and C3. Okay? Similarly, we can find C1, C2, and C3 by using the same determinants. But now we're going to go one row down. So let's go and do C1. So C1 equals the determinant of these over this value, right? So now we're working with this over this value. So C1 is the determinant of 1 W0 squared plus 2K alpha. And then we're going to have this value, which is K1 minus 2 alpha and K alpha squared, right? Over this value, which is K1 minus 2 alpha. So now let's determine what is the value of C1. When you solve this equation, you're going to find that C1 is going to be equal to, so you cross multiply as we did before, and we're going to find the value of C1. So let's cross multiply real quick here. So we got K1 minus 2 alpha, W0 squared plus 2K alpha, minus K alpha squared. Okay? Divided over K1 minus 2 alpha. So if we separate this, if we just have this expression divided by this, we're going to get C1 is equal to W0 squared plus 2K alpha. And let me just put this over here. And then this other section will be minus K alpha squared over K1 minus 2 alpha. So with these, we're going to get a more simple result for C1, which is going to be basically C1 equals WC squared plus 2K alpha minus alpha squared 1 minus 2 alpha. Okay? And that's the value of C1. Now, please notice here, C2 will have to be the determinant of these and these, therefore it's going to be 0, and the same for C3 is going to be 0. So we are going to have C1 with this value, and C2 and C3 are going to be 0. So now, let's complete this matrix. So we know now, I'm just going to rewrite the matrix the following way. So we have for x4, k plus w0 squared, k alpha squared, as we have here. S to the cube will have the following coefficients, w0 squared plus 2k alpha and 0, and we have here. And then s squared is going to be k1 minus 2 alpha, k alpha squared 0, as we have here. S to the 1 is equal to c1, which is w0 squared plus 2k alpha minus alpha squared 1 minus 2 alpha. C2 is 0, C3 is 0. And now let's find s to the 0. Okay, now to calculate the coefficient when s to the 0, we're going to do the same process. So we're going to get the determinant of this section divided by this. So let's do that. So we have k alpha squared multiplied by w0 squared plus 2k alpha minus alpha squared over 1 minus 2 alpha. By this multiplication equals 0, so we're not going to consider that, and then divided by w0 squared plus 2k alpha minus alpha squared 1 minus 2 alpha. So notice that these two terms can be cancelled out, and this coefficient is going to be equal to k alpha squared. So now we have completed the process, and all we need to now focus on is on the first column of the Routh array. So we're going to focus on this first column only, right? And all of this column has to be greater than 0. So now with that, we can find the values of k, the ranges of k. Notice that in s squared, k 1 minus 2 alpha has to be greater than 0. So that's very simple. We just substitute the value of alpha, with the problem give us is 0.25. So we just end up with an expression of the following form: 1 minus 2 by 0.25 greater than 0 by k. So k 0.5k has to be greater than 0. So k has to be greater than 0 in this term. Now this term, let's find out what the k value has to be to make this term greater than 0. Okay? So we know that if we substitute alpha, we will have something like w0 plus 2k 0.25 minus 0.25 squared 1 minus 2.25, and basically this is equal to 0.125. This section is equal to 0.125. So we're going to have w0 squared plus 0.5k minus 0.125. It has to be greater than 0. So let's solve for this equation here. So if we want to find k, so let's move some of the terms to the right. So we're going to have basically 0.5k has to be greater than 0.125 minus w0 squared. Okay? And we just have to divide by 0.5 to get k, so let's do that over here. K has to be greater than 0.25 minus w0 squared over 0.5, which is also equals to k has to be greater than 0.25 minus 2w0 squared. So